Low Earth orbit is becoming a high-speed minefield. Thousands of defunct satellites, spent booster rockets, and discarded fairings are currently circling the planet at over 17,000 miles per hour. This density makes the Kessler syndrome a statistical certainty. It is a chain reaction where one collision creates a cloud of debris that triggers further impacts, spiraling into an unstoppable wave of destruction. When these metallic bodies collide, they don't just stop, they fragment into thousands of tiny, untrackable pieces of shrapnel. At orbital velocities, even a marble-sized bolt carries the kinetic energy of a hand grenade. Without intervention, this cascading debris will eventually surround Earth in a shell of lethal hardware, making the launch of future satellites or crewed missions far too dangerous to attempt. To stop this, engineers have proposed a fleet of space tugs, specialized vehicles designed to rendezvous with junk and push it into a decaying orbit to burn up in the atmosphere. But the economics of orbital cleanup are punishing. Every kilogram of hardware launched requires an immense amount of infrastructure and fuel just to leave the atmosphere, driving the initial mission cost into the hundreds of millions. Once in space, a tug must constantly burn propellant to change its inclination and match speeds with target debris. This maneuvering is the most energy-intensive part of the mission. This creates a terminal roadblock. Once a space tug exhausts its propellant, it loses the ability to maneuver and becomes part of the debris problem itself, requiring a second, expensive mission to refuel it. Using traditional chemical rockets for cleanup is unsustainable. The mass of the fuel required to move the debris often exceeds the mass of the debris being removed, making the logistics of large-scale cleanup impossible with current launch capacity. This forced engineers to look for a different solution. What if a cleanup vehicle could generate its own propulsion from the environment around it? The solution is a debris recycling space tug. This vehicle is designed to treat the orbital debris field as its primary source of fuel. The tub uses a funnel or a physical capture system to swallow small pieces of metallic hardware, bringing them into an internal processing chamber. This design changes the fundamental logic of spaceflight. Instead of a mission being limited by the fuel it carries from Earth, the presence of more space junk actually provides more opportunities for movement. To process the junk, the tug deploys massive solar arrays, capturing sunlight and converting it into electric power to run the internal systems. This electricity powers a microwave magnetron or electric induction coils. These components use electromagnetic fields to bake the captured junk with intense, concentrated heat. As the metal reaches extreme temperatures, it undergoes a phase change. The solid aluminum and steel are stripped of their electrons, causing the material to ionize. The result is a cloud of superheated, highly charged plasma, the same state of matter found in stars and lightning. Finally, powerful magnetic nozzles guide this plasma, expelling it out the back of the engine. This high-velocity exhaust provides the thrust needed to maneuver. By recycling debris into plasma, the tug maintains a self-replenishing propulsion cycle, allowing it to navigate from one target to the next without a resupply ship. Because the tug is powered by a self-replenishing propellant source, its mission duration is limited by mechanical wear rather than fuel capacity, allowing it to remain active for decades. This longevity allows for dual-duty missions. The tug can use its continuous thrust to intercept massive, intact satellites and push them into higher graveyard orbits, safely out of the way of active commercial lanes. While moving these larger payloads, the tug continues to collect the small, ambient fragments it encounters along the way to keep its plasma drive energized. This creates an orbital janitorial system that becomes increasingly effective in cluttered regions of the atmosphere. The scale of the cleanup is massive. This map represents the millions of trackable debris fragments currently in orbit. For a single tug, clearing this field would take hundreds of years. However, a coordinated fleet of 50 debris recycling tugs changes the timeline. If this fleet consistently collects and deorbits material, projections suggest the Kessler threat could be significantly neutralized within 15 to 20 years. Solving the debris problem this way proves that we can sustain complex missions using the materials we find in orbit. It provides a practical blueprint for long-term space logistics, where the resources needed for exploration are harvested directly from the environment.